So welcome everyone to the ilifu online training workshop. So this is a follow-on from a basic training workshop that we ran 2 weeks ago. I'll just introduce the team presenting. So I'm Jeremy Smith. I am the operations manager at ilifu, and then Jordan Collier, whose video is on, is astronomy support person, and Dane Kennedy is the bioinformatics support person. So today, Jordan and Dane will be presenting different sections. Before we start with the presentations, I'd just like to run through the support channels that we offer. First of all is we have a support email address at support@ilifu.ac.za. So communicating, this is the primary communication channel or support channel for us. Your emails will go to a ticketing system, which is accessible to all the support personnel. So it's the best and the fastest way to contact us. We also offer ilifu user documentation at docs.ilifu.ac.za, the link on the slide. So this, I'm just going to switch to the documentation. Nope, that's not working. Okay, so this is the example documentation. So just a quick run through the landing page. We've provided a step-by-step tutorial guide in the getting started section, which takes you through the basic steps of using the ilifu cluster. And then there's additionally technical documentations which have slightly more advanced topics, which a lot of the topics today are covered in this section. For example, the software environments for RStudio and running using R, as well as topics about CARTA and the IDIA pipeline or under astronomy, as well as in the submitting jobs for SLURM, under specifying resources. You can find a lot of information on the parallelization of jobs on SLURM, which Jordan will go through. So that's our user documentation. We also have a ilifu system status page, which provides information about the status of the system. So this is a good first point of information when you're running into an issue. If there's a specific service that has a problem, we would indicate that issue on this status page at status.ilifu.ac.za. So you can drill down into different services and look at the state of those services. And then finally, we have the training videos. So just to indicate that this training session is being recorded. And the training videos are then uploaded onto our ilifu website under the training section. So we have last year's and the previous year's videos already available. And once we've completed the workshop series, we'll work to uploading the new videos as well as the presentations onto the website. So I just introduced the topics for today. Dane is going to start and introduce Python virtual environments and using R and RStudio. And then Jordan Collier is going to talk about parallelism on the cluster, advanced SLURM usage, talk about pipelines, data transfers, as well as CARTA, and cover briefly best practices. So I'm going to hand over to Dane. Sorry, Dane, before I go on, we have a lot of information to cover. So what we're going to do is we're going to have a Q&A session after the presentations. So if you're welcome to post questions into the chat, but we'll open the forum to questions once the full presentations are complete. So that will be about a 15-20 minute period available for questions where you can ask us directly if you've had any issues or if you want to know additional information about any of the services or the ilifu cluster. Cool. Thank you.
Yeah, so my name is Dane, and as Jeremy said, I mostly support the bioinformatics users, but I do one or two other things, like I help Mike, who's also here, with a bit of the SLURM administration, and then we've got a reporting website, which I don't think has been made public yet, but I'll also do that. But yeah, so today I'm going to cover 3 topics actually. I hope you guys haven't covered modules before, I don't think. So I'm going to quickly mention environment modules, and then Python virtual environments, and then R and RStudio. So it's a little bit of extra context in terms of astronomy and bioinformatics. A lot of the software and tools that you'll be using have been written in Python and R. I think maybe R is bigger in the bioinformatics world, but I think you do use it a bit. And so what I want to talk about is how to use them effectively in a cluster environment so that you can keep your analyses clean, and when you're doing different jobs on a cluster, you don't get things confused and making one job break another job. So the very first thing I would like to talk about is environment modules. So environment modules are a way of setting up your Unix environment in a predictable way so that the software you need is readily available when you need it. It's particularly valuable in situations like a cluster where one needs to make multiple versions of the same piece of software available. So for one analysis, you might need Python 2 for some reason, and otherwise you might need a specific version of Python 3, and environment modules allow you to do that. So quick summary of the main commands that you'll need to be aware of are module avail, which lists all the software that's available on the cluster. This is quite an outdated list. There's a lot more available now. Then there's module add, which sets up your environment so the software is available. So in that little demo that you can see there, first I start trying to run R, it's not there. We add the module, and then magically R 3.6.3 is available. And it's really as simple as that. I think Jordan wanted me to show you some of the astronomy software and the help systems available. So there's another command which I haven't written in this note, unfortunately, is I'll add it for when we upload the slides, but the command module help and then module name. And then it gives you a little bit more information about how that environment is set up and commands that are made available when you use the module. Yeah, so then to talk about, I'm going through very quickly, and I do encourage you to read our documentation that Jeremy already pointed out, because I think everything that I could say is probably said there better, but hopefully this just gives you an idea of what's available there. So virtual environments, if you haven't used them before, are a way of setting up a specific Python on your machine or on ilifu's SLURM cluster, so that you can install packages in such a way that they're exactly what you want. And this is often important, as I said before, if you're running multiple different analyses that have different requirements. I think another way people often install software is using pip install -- user. And the problem with that is you end up with conflicts. So you have 2 different pieces of software that have a different requirement higher up. And then those installing the latter package can break an earlier package. Yeah, so it's a fairly simple command. Once you've loaded up I'll show this as an example of this later, but once you have your Python on the system, it may be the operating system's Python, or it may have been activated through the use of an environment module. You simply run the command virtualenv, and then you can give it a name, and it'll set up a Python there that you can then use. The environment needs to actually be activated. So in here, the example, an environment called virtualenv has been created. Then the command to activate the Python is to source that file. If you're not familiar with sourcing, is basically there's a normal bash script underneath there, and it runs all the lines of that. And it just sets up the paths to the executables and the libraries in much the same way that modules do, actually. And so once that file has been sourced, the Python is then available. And I don't know if you're familiar with the which Python, but that tells you exactly which binary will be run when you run that command. So yeah, after that, you can start installing your specific software as you would normally with a pip. And then to exit your new virtual environment, you just run the command deactivate. And then you'll be using the system Python or the one that you made available with the environment modules. I think you guys covered Jupyter in the basic training. And within Jupyter, I don't know if you remember, but you can have different kernels available. And one of the things you can do is if you've set up a Python virtual environment, you can then make that available to Jupyter. And it's as simple as first activating your environment, as we saw on the previous slide, and you need to install Jupyter. And then this is the magic command, ipython kernel install, and you give it a name, and you specify -- user so that it installs within your home directory. It sets up a directory like that, and within there's a little kernel.json file, which basically tells the Jupyter Hub where to find the Python binary that you'll be using, which is your virtual environment you set up. And then if you go to Jupyter Hub, you'll find magically your new Python kernel is available there. And there are quite a few kernels already available in the system. So most of these are standard and you'll have access to, but I think you must have seen that in the basic training. So that's essentially Python virtual environments. And the other thing I wanted to talk about is R. So there are a number of different ways that R is available on the system. The two main ones are just a raw R, which I show in this slide, and that's installed natively on the cluster and made available through a module. So you can see here, I'm starting an interactive job. I say module add R 4.0.3, and then R is available. And that's, you're probably reasonably familiar with that version of R. And then in a job, you do much the same thing. You say module add, and then your R will be available. Yeah, I don't think there's too much more to say about that, except that the other way of accessing, or one of the other ways of accessing R is via RStudio, which is my personal favorite IDE. And this is outlined in more detail on the website once again, but there's a module with RStudio in it. And here what you do is you add the module within a job. I don't think you can do this you wouldn't do this in an SBatch job, so it has to be in an interactive job. And you then just run the command RStudio. And what it then does is it outputs a whole bunch of information that you need to then run on your local machine, so not on the cluster, in order to access the RStudio server, which will be running on a node on the cluster. So I didn't have enough space to put the entire command, and I'll show you this in a demo later, how it actually works. But you can see on the right panel, that's actually RStudio running on a compute node but made available on my local browser, which I think is quite an amazing thing. And just a quick note, we get lots of questions on help desk about how to install packages on R, or we get requests to install the packages, but R does actually make it possible to install your own packages, and then they just get stored in your home directory. Mostly when people are battling to do this, it's bioinformatics users who are using the wrong command, and they're using install.packages rather than the bioconductor install command. I quite like the bioconductor install even for non-bioinformatics packages, because it does tend to update the whole dependency tree for other packages as well, if you've got a big complicated environment. As far as I know, R doesn't offer a similar packaging system as Python in terms of like a virtual environment, but I think it manages dependencies fairly well. I certainly haven't experienced many packages breaking other packages. Yes, and the final way to access R is actually in Jupyter. So we've added the Jupyter kernel, and that's available in Jupyter Hub. Yeah, then I was going to do a quick little demo just to show off RStudio and virtual environment modules. Stop sharing that one. Start sharing. This one. Okay. So here I've logged into the cluster. I'm going to start an interactive job. There we go. I've been put onto compute node 003. So looking at environment modules, I'd say module avail, and it'll show me a list of all the packages that are available. They're vaguely compartmentalized into commonly used things, so none of these are necessarily very specific to your discipline. And then they're Astro packages, and they're bioinformatics. And then if you happen to be part of CBio, you might see another whole section. But essentially, this is everything that's available. If you're looking for something, you can use, say, module avail, and then you can give it a name, say RStudio, and then it gives you a shortened list where it's found RStudio in the name. You shouldn't get this doubling up of stuff like I do. That's something buggy in my environment. So then an example of running RStudio. So we've found our module that we want to use. We say module add. We give it our RStudio. It's got the highest version number because newer is better. And we run RStudio. And then we would just say our server, RStudio, pardon me, studio. And then I'm going to hope none of you are evil, because it's going to flash a password, but it won't be live for very long. So it's created an environment, and it's given me a password, and it tells me I need to go to this URL, and I need to, well, I first need to, sorry, SSH to this node. So we go here, I go SSH to there. And now this is running on my local machine. So now it's connected to compute 003 using via the login node. So that's what this proxy command whole thing is doing. And it's set up, it's listening on port 8081 on my local machine, and it connects to this port, which is the one RStudio has set up. And then I can go to this URL. And now I'll need to stop sharing and open my browser. share it again. Hope that's the right screen. And then I use my name, password. And now I'm running RStudio on the cluster on my local machine, which I think is quite neat. And that's about all I have to tell you guys. Please let me know if you have any questions, because I'm sure I mumbled a lot. And over to Jordan.
Thanks. Yeah, there'll be time for questions at the end. Cool. So let me share my screen. Thanks, Dane. Okay, so you can see my full screen there, hopefully.
Yeah, we can, Jordan.
Cool. So thanks, Jeremy and Dane. So as Jeremy mentioned, I'm Jordan Collier. I'm the ilifu support astronomer. So together with a growing team of support astronomers, we're the first point of contact for the astronomy users using the ilifu facility. So I'm going to be starting by talking about advanced SLURM usage. So this builds on top of what we talked about in the basic training 2 weeks ago, for which you'll see the recording quite soon, or you can already access last year's and the year before's recording. So this is what we talked about last time, just to reiterate this quickly. When you SSH onto ilifu, what you do is land on the login node. And this is essentially for job submission and management. We could also call this the head node. And what you want to do here is run your SLURM commands and submit your jobs, but not do your heavy processing and run your software there. The place you want to do that is on the compute nodes, also known as worker nodes. And this is where your processes run. So you run your SLURM commands, it will submit jobs that then run on the compute nodes. And generally this is done by Singularity containers. So in this schematic, you can see we've got the login node. We have 2 examples of partitions, and these are essentially groupings of compute nodes. So in the main partition, we usually have about 80. And then in another partition, like the Jupiter spawner, we've got 12. And then just to go into a little more information about the different partitions, you can call the command sinfo to give you this information. But right now, for instance, we have 70 nodes in the main partition. Each has 32 CPUs and 232 gigs of usable RAM. And then we also have a high mem partition with 2 nodes. Each of these has 32 CPUs and 480 gigabytes of usable RAM. And then lastly, we have a GPU partition with 4 nodes. Each of these has 2 GPUs and has 32 CPUs, 232 gigs of usable RAM as well. And so these you can see with sinfo, and you can use that information to see what's available and where you might want to submit your job. And so just to outline the kind of compute workflow and these different environments and what they're appropriate for, as I say, you land on the login node. This is where you should run your SLURM commands, and you might run basic bash commands here too, like changing directory, making a directory, listing its contents, and so on. And then we may also make use of Jupiter. And this is generally a development space for running new code and workflows and routines. Perhaps you're debugging or testing your software, and so maybe it's likely to crash, and you don't really want to make use of the main partition to have a job wait in the queue and then crash quickly. And so there's very much a development space. We're also exploring the idea of a development node, which is like a shared node similar to a virtual machine where many users would SSH in. And this again would be like for a development space and for debugging and testing software. And then on the main partition, generally you're running your computationally heavy processing here, and this is for stable routines, not for debugging and testing. But once you have your routine, your workflow in place, you'll generally run it on the main partition. You may also make use of the high mem partition, and generally this is for where you have a single high memory job that can't be split into multiple jobs by what we call MPI, message passing interface. I'll cover this later, But essentially, if you can't make use of that to split your job into multiple steps that each take a smaller amount of memory, then if you have high memory requirements, you would want to use this partition. And then we also have the transfer node as a service. This is for internal and external copying. So from one path to another within ilifu, or from an external machine to ilifu, or vice versa. And I'll show this on a later slide. And so to cover some of the advanced user commands, you can head to this URL and see some of the syntax involved there. It shows the long and short form. So the short being like this here, option O, and the long being the double dash partition, option partition. And yeah, this is shown within the documentation. I suggest you go there, but here are some selected user commands to cover in this workshop. So before running a job, you ought to identify the resources available. So you can run sinfo, you can pass in these parameters to see what's available. You can also run saccount manager with this syntax, and this shows your accounting group. So these are the projects that you belong to, and you should identify which project you're submitting your job under, so that it helps us with collecting the information about usage, but then also, you know, if you want to be able to continue with fair share usage over all the projects, then you ought to be specifying which accounting group each job is submitted under. And then for srun and sbatch, we can run something like this, run a job on the main partition using this accounting group that I belong to. And this would be the job that we want to run. So this, I think that's actually, yeah, that's a bash script, for instance, that I would want to run there. And then I've also got this call to submit to the GPU partition, and this is the syntax that we use for that. Some other advanced commands. So you would want to use your job ID, for instance, to run some of these commands. And this is what's given to you upon submitting a job. So ideally, you're doing this via sbatch, and the job ID is output to the screen for you. Or if you lost it, you can go to SQ and see your job ID, or saccount, or another one of these SLURM commands to get it. But for instance, if your job's running, you can run scontrol show job ID and then the job ID, and this shows quite extensive information about the job that's running, including the working directory. And then for a short period after the job's run, this is also available. What continues to be available indefinitely after your job is run is the information via saccount, also available as your job is running. And this is quite an extensive list I've provided of parameters that I want to get from a job that's running. So for instance, the job ID, the name, partition, an account that it belongs to, how much time has elapsed, the number of nodes, tasks, and CPUs that are being used, the maximum disk read and write, the list of nodes being used, the max RSS, which is the maximum memory spike, the CPU time, the state and exit code. And then this percent and number just means to pad the output column, usually to be something larger so that the contents fit within the column. And then the negative is just like a formatting thing. So this shows quite useful information for multi-CPU jobs, and is basically my default for looking at the information for a multi-CPU job running. We can also search for historical jobs that no longer appear in saccount by default, since that only shows generally jobs that have run that day. So we could say start time and then a start time and an end time. So option S and E. And this will show the jobs within that time frame that belong to me. Option X just means print one job per line, rather than the default is one line per job, rather than multiple lines per job as the default. And then I've outputted similar parameters to before. Or for instance, if I want to look at a job that ran on one of the old clusters, since we still have that database as accessible, we could specify the job number, and then the cluster equals ilifu SLURM. So this was the original cluster. We also have ilifu SLURM 20, and then the current is ilifu SLURM 2021. So I could look at jobs that I ran on the old clusters with that syntax. There's also an ability to email yourself. So along with a number of other stuff, you can see this in the documentation here, particularly at the bottom of this page. You'll see a whole bunch of arguments and the syntax and information about it. But for instance, I will put mail user equals and my email address, and then mail type equals, and then a comma separated list of events. So for instance, we may want an email to notify us when the job's begun, when it ends, when it fails, or if it hits the time limit, if it runs out of time. We can also exclude nodes. For instance, if we know that a node is problematic, which we would request that you please report to us. But in the meantime, after reporting, and if you want to run your routine straight away, you can use the exclude parameter and then use compute, and then this kind of syntax for a comma separated list or a range of compute nodes. There's also something we can do called an array job. And essentially, array jobs allow for quick submission of many similar jobs, each with the same resources, without the need to go and manually launch every single one. And the ideal behavior here is that you'll pass a task ID, which is the thing that's changing in your array job, and that would change the behavior of each of the different jobs that run. For instance, you're providing a different input selection. So I'll go on to describe this more, and it should make more sense. But another use case is to run several related steps in a serial process by only letting one array job run at a time, and each completes and then runs the next. But in general, we would suggest that you use dependencies for this, which I'll talk about in a moment. So the main use case is to run many at once, each slightly different, but using the same resources. And so the syntax here, if we're running this within an S batch job, is shown. So the argument is array equals, and then I have an example of 1 to 20 with 5. So this means run 5 concurrently, 5 simultaneously, but then a total of 20. And then I've emailed myself when it fails, or I believe this syntax from memory is to email me when each separate array job launches. And so this is going to run 5 at once. And then the important bit is that I'm passing as input the SLURM array task ID. So this is the thing that changes each time a different array job is run. And so I might have some script that handles that input. An example might be in Astronomy, I'm imaging a cube, so many different channels over frequency within a cube. And I may want to image 20 with 5 at once. And my script takes the channel number as input. So the first would image channel 1, and then so on. And so this is the way I can launch it within a single array job that handles doing all of them concurrently. And then this brings me to environment variables and substitutions. So this, what I showed down here, was an environment variable. This is something accessible within the SBatch script that refers to something related to the SLURM script. So you can read about these here, but essentially the environment variables are listed here. And then there's also a way to substitute variables into a file name. So for instance, a log that you're outputting, you may want to know the job name, the job ID and job name, and you may want to substitute that into your output file for the standard out and standard error. And so we've got %J for the job ID, %X the job name, %A if it's job array, that's the master job allocation number, and then %a for the task ID, that's the one that iterates. And then we also have CPUs per task, which is important if you're doing multi-CPU processing on a single node, since you may want to export OMP num threads to do that, which I'll talk about a little bit later. So if I just go back, for instance, you could see in my output, I've used %X dash, and then essentially this will give job name dash job ID underscore task array ID. So every single separate task that's being run within the job array has a different and unique standard output and standard error log. And then, moving on, this is some of the advanced usage for running an interactive job. So in general, if I specify a lower wall time, lower memory, and lower number of CPUs, I increase my chance of the job launching immediately. So here I use the example of running the radio astronomy software CARTA, but it's the same kind of syntax for any processing. So if I want to do an interactive job in steps, I can srun pty, and then I only want to run for 10 minutes with 1 GB of memory. Again, this increases my chance of getting resources immediately. Then I say bash, and this will put me on a compute node where I can run Singularity and shell into a certain container. And then this specific call for CASA to launch an interactive CASA session. I could even do this in a single call, which is basically the same syntax all kind of packed into one call, and then using just a slightly different format for hours, minutes, and seconds. But then after this, I must manually process, which is somewhat problematic because it's, I guess, a little volatile. So in the previous srun example, your job is running in a bash session, it's outputting everything to screen. And yeah, srun, and even if we use screen and tmux sessions or even mosh to allow for intermittent connectivity, we can run the job interactively in this way, but I guess this is subject to restarting the SLURM login node, which happens from time to time. So if you have some interactive process running like that, and we do have to restart the login node, then your job would be killed. So what's actually best is to write an sbatch job. It runs in the background, it writes the log files that you can later access and read, rather than trying to find it in your terminal screen output. And then this runs on the compute node and is not subject to restarting the login node. And so here's the same example as before, but packed into a sbatch job and then run for an hour, which is perhaps a bit more typical for these routines. And then I run that via sbatch and then the name of the sbatch file. And then lastly, for advanced SLURM usage, dependencies. So this is essentially where a job can be scheduled for running based on the status of a previous job that's been launched. So for instance, you may only want to run this job once a previous one successfully completes. And the syntax for that is sbatch and then option D for dependency, after OK, colon, and then the job ID. And then you can say kill on invalid dep is yes. This just means if this particular job that's a dependency crashes, doesn't complete successfully, then kill this job that I've submitted to the queue. So it doesn't just sit in the queue and never run. It will cancel the job. And then we can also use this after any syntax and even pass in a colon separated list of job IDs, same as with here, you can do that. And after any just means submit this job after the dependency is complete, whether or not it was successful. So any exit code. So that brings me to parallelism. This is, this schematic here is kind of something I introduced in the basic training, but essentially talks about the way that we've moved from being able to do all your processing and visualization and everything on your laptop to perhaps using a virtual machine or a server, to moving on to a cluster where you've got a job management and scheduling software like SLURM. And this is very much, I guess, the language. So we're talking about, when we say a node, we're talking about a single computer or server or virtual machine, or even machine or box. And a cluster is talking about many of these connected together. Each has its own RAM and CPUs, and some processors can make use of multiple at once, as I'll go to talk about. And so this is very much talking about parallel processing, and the Oxford definition for this is a mode of operation in which a process is split into parts which are executed simultaneously on different processors attached to the same computer. Or I would add, in our case, or different computers attached to the same cluster. And so what's done is the work is partitioned into smaller jobs. Usually the data itself is partitioned into chunks, and each of the smaller jobs or workers receives that partition of the data set and does its operation. And so there's different ways to achieve parallelism. If you're doing so on a single node, then you're distributing the work over many CPUs, restricted by how many are on that node, in our case 32. Typically, this is implemented with OpenMP. If we're trying to process over multiple nodes, then we're distributing our work over many tasks. And we can, in fact, do this with just one node over many tasks. And each is given an amount of memory to use. Generally, we're talking about doing this on a cluster and using OpenMPI, message passing interface. And this requires an MPI wrapper like MPI run, AP run, SLURM's srun, or the CARTA radio astronomy software uses MPI CASA. And on SLURM, on ilifu, we can achieve this through SLURM. And so here are some examples, just expanded a little. So for instance, just firstly to say that a normal job would actually use one CPU, one task, and one node. Much software doesn't support parallelism, so you first need to ensure that your software can support this before you try and attempt to do this kind of parallel processing. So for instance, we may want to do an OpenMP job in SLURM, so we would set our CPUs to be more than one, while tasks and nodes must remain as one. Unless you're also using MPI, which some software does, but not many. And so in this case, we would set CPUs per task to be more than one. And we may want to export OMP num threads to be equal to the number of CPUs we're using, as I showed earlier. We could also implement an MPI job on SLURM. This is where we'd set tasks to be more than one, while nodes and CPUs could be set to one or could be more than one if it supports multiple CPUs and multiple tasks. So here we're setting nodes, n tasks per node, and CPUs per task. And you need to wrap this in an MPI call. And for all of these, the product of your task per node and your CPUs per task cannot exceed 32, since this is the number of CPUs on a node. So here's this in SBatch form. So using a single node with many CPUs, we set CPUs per task to be 8, mem per CPU to be 1, and then we have our call as shown earlier to run our process. We could do a single node with many tasks. So we set tasks to be 16, leave CPUs and nodes as 1, and then we have our MPI wrapper and then our singularity call and the script. We could also do many tasks over multiple nodes. So nodes is 2, n tasks per node is 8, CPUs per task is 1. And then we've got mem is 10, and this is per node. So overall, since we have 2 nodes, this is 20 gigabytes allocated. Then our MPI wrapper again. We could use many tasks and CPUs within one node. So nodes is 1, n tasks per node 4, CPUs per task 8. So this uses all 32 CPUs. And this is an example of using the CASA radio astronomy software. So we have our MPI wrapper, singularity call, the path to the container, then CASA, and then our script that we're passing in. Okay, so what I want to very quickly, because we're running out of time, sorry about that. I want to very quickly just demonstrate the IDIA process meerkat pipeline, not to demonstrate anything about radio astronomy, but I guess to show a good framework for how you could write these kinds of jobs within a pipeline and be able to separate out the steps that do and don't make use of MPI. So just going to really quickly SSH. So this is the long form for connecting to the SLURM cluster. And so from here, luckily I looked at this earlier, so I'm just going to go here. So this is, I'm not going to explain this in detail, but this is essentially a call that I can make of this particular software. And what I'm doing is passing in a raw data set, and then I'm making use of a particular accounting group. I'm asking for half an hour of time per job that I'm running. And then in this case, I'm making use of a reservation, which is essentially so I make sure that this actually runs right now. So this happens to create a config file. And the important thing I wanted to show here is that it has a path to a container, an MPI wrapper, it has the accounting group, and then it has a list of scripts, and then associated with all of these is true or false, which means this does or doesn't run MPI. And then it has, in this case, an empty string means use the default container. The last one uses a different container. So this is essentially a framework I'm showing where multiple steps can use different containers and they can either use MPI or not. And so what I then go and do is run that, and that's essentially created a bunch of SBatch scripts. And so for instance, here's one that didn't make use of MPI. And so I've got these all set to 1. And then here's one that does make use of MPI, and this also makes use of an array job. So I have my array job syntax. I've got ntask per node is 9, CPUs per task is 2. So this uses MPI and OpenMP. And so I have my MPI wrapper, and then singularity call, and then the Python call. And the order here is important, actually, that your MPI wrapper must be outside your singularity call. That's the suggestion here. And you can see that I'm using the task array ID to go into different directories and run the same thing within, in this case, different frequency windows. And so that's just a quick example I wanted to show for a good framework for designing your own pipeline and being able to make use of different resources for different kinds of jobs and potentially different containers as well. I lastly want to cover data transfers, and then very quickly CARTA, Astronomy visualization tool. So data transfers are documented at the URL there. A reminder to please not use the login node to do data transfers, as this will be something that affects all users and could negatively impact what they're trying to do. And then again, please don't write large files to your users directory, only generally scripts and config files. So once you're ready to do your copying, you can make use of the transfer node, transfer.ilifu.ac.za. Here you would run copy or secure copy or rsync, as I said before, either internally or externally. And here's the kind of syntax that you could use for a transfer from, say, your machine to ilifu. And then Globus is suggested for either larger or more frequent transfers. It's faster than SCP and rsync, and it uses a dedicated data transfer node. So yeah, this is something that's set up, for instance, between Soreo and IDIA, which is where the raw data for the Meerkat telescope comes from. So this is something that you won't necessarily make use of, but will benefit from. But then you can also use it between your own machine or between other servers and ilifu. It's got a very user-friendly user interface built on top of GridFTP via Globus. So it has this web app. It also has a command line interface. You can connect it to any arbitrary endpoint, such as a server, your own desktop. It has versions for Mac, Windows, and Linux. And so while it's very computationally efficient, it's also very user-friendly. So this is something I encourage you to investigate. You can find it at the URL there. It's got information very straightforward about how to install it on your desktop and how to log in to the web app and make use of it. So lastly, I want to cover CARTA. So this is an astronomy visualization software, and it's a collaboration between IDIA, the NRAO in the US, and then Asia A in Taiwan, and essentially a cloud-based visual analytics and remote large image cube software. So it's particularly aimed at big data, and it solves a lot of the problems to do with visualizing terabyte scale data, for instance. It can do so quite easily. It supports many different image formats. You can read our documentation here, and this describes things like, similar to what I've listed here, how to access CARTA. So it's at that URL there, and you use the same login credentials as you would via the Jupyter spawner. It only has the CARTA share file system visible. So this means you either have to copy or convert your data and put it in the CARTA share directory. So in general, we recommend that you convert to the HTF5 schema. And there's syntax listed here for how you would do that. You essentially take a FITS image format. You can convert it to HTF5 and then put it in your CARTA share directory. So just quickly, I'm running out of time, but just to give you a quick demonstration of CARTA. So this is where you will land when you go to that URL. You'll log in. You'll be, by default, it's not in dark mode. You'll be presented with the file browser, and then say you might want to open a image. Hopefully I don't get in trouble showing this. I think this is a cube that we were working on, so you can pan around, you can zoom in and so on. You can look at the X and Y axes, you can look at a Z profile. This particular one, I guess maybe isn't a cube. Yeah, there's a whole bunch of things you can do. I guess I would suggest at this point that you go and look at the training from last time if you want a bit more of an extensive demonstration, but it is very user friendly, and you should be able to do a lot of things quite intuitively within CARTA. So go and check that out if you'd like to, or otherwise just connect and have a go yourself if you haven't already. And feel free to reach out to the support team if you have any questions. So the last slide here, best practices, just to reiterate a few things. So as I've mentioned, please don't run the software and heavy processing on the login node or the copying. Only submit jobs and run SLURM commands from here. Please use the transfer node or Globus to transfer data. Before running a job, identify the available resources, use sinfo. In general, if you can reduce your allocation and not hog the cluster, then that's recommended. But obviously there are times where it's appropriate for a project to make quite extensive use of the cluster. But again, if you want to increase the likelihood of your jobs running immediately, then request less memory, less wall time, fewer CPUs. And in general, we suggest you use SBatch. As I mentioned, those other methods are volatile. Please clean up your data that aren't needed. If it's old raw data, temporary products, maybe scratch data, then it's very helpful for us and for all the users if you go and clean that up. Obviously, we're not trying to hamper your research, but we're trying to ensure that everyone can do their projects. And the way we do that is by people cleaning up their data. Please don't place large files in your home directory, and please generally use Singularity, since you generally don't install software on the nodes, although obviously, like Dane showed, Python virtualenv could be used, or perhaps you can get in touch with us and we can add software to your container or build a new container, or there are other methods, but in general, you make use of Singularity. So please have a look at the documentation for doing that. That's my last slide. Thanks for listening. We probably have a moment for a couple of questions. If you do need to go, it's almost the hour, so please feel free to jump off, or if you want to type your question in the chat, we could then cover it and you can watch the recording later. So thanks for listening.
Fantastic. Thanks, Dane and Jordan, for your presentations. So we'll open the floor to questions now. I'm going to start with going through what has been mentioned in the chat in case anyone hasn't been following the chat. So one of the queries was about Dane using ZSH instead of a bash shell. So that's just Dane's personal preference in terms of a shell, and it's perfectly reasonable to use bash or other shells, including ZSH. I think there's just a certain level of extra power or customization that you can implement with ZSH that Dane enjoys. The next question that was asked, which has been answered in the chat, but I just wanted to bring it up for everyone's attention, was what kind of jobs would you use GPUs for as opposed to CPUs? So Dane responded initially just that not all jobs are suitable for GPUs. In fact, unless you know for sure that a job or your software is optimized for GPUs, it probably isn't. So he speaks mostly bioinformatics tend to not use GPUs, but there are a couple of chemistry, computational chemistry kinds that are good. Specifically mentions, I'm just going to scroll down to single instruction, multiple data type jobs or analysis is helpful on GPUs. From an astronomy point of view, the same thing follows in terms of it really is dependent on the software that you're using. So there are a lot of machine learning packages that benefit from GPUs because of the type of data that they're running. And there are opportunities like using some examples are like TensorFlow has GPU capabilities. So it does depend on the data, but it can significantly improve performance of your jobs. But again, the software tends to be built for GPU or CPU usage. If you are interested in using the GPUs, we haven't actually announced this yet, but we've been developing, providing a GPU nodes in the Jupyter environment. So you are able to select a Jupyter interface that has a GPU resource underlying it. So that is an option. But we will send out an email about and update our user documentation very soon about that. That's quite a new development. Just going through the chat. Does Dane and Jordan, you're welcome to add anything to what I've said already.
I'm not sure if you mentioned some of the astronomy software. So there's, for instance, a WS clean version that can make use of GPUs for imaging. And then there's Pink, for instance, that's like a self-organizing map software. Yeah. And that's much faster with GPUs. So that's some of the software where you may be interested to make use of the GPU resources.
And then just to mention again that the recordings will be made available. We'll post them on the website along with the PDF presentations will also be made available for everyone. And the previous year's recordings and presentations are currently available.